So far, we've been dealing with a lot of circular motion problems, but they've all had one thing in common, and that is we haven't actually had any forces at angles. Okay, that doesn't mean though that they don't exist and that we can't do them. So we're going to take a look, spend a little bit of time looking at circular motion problems involving forces at angles. And one really, really important case of this is the banked curve. Okay, and we see banked curves a lot, particularly on tracks, whether it's a bicycle track, a NASCAR track like we have in our picture here. Even some tracks for people running on them when they're an indoor track actually will have a banked curve. And so rather than the curve being level, it will actually have some angle to it, and that helps to create that inward force that we need acting on the object to make it move in a circle. If any of you run track at all or do some sport that involves a track with a banked curve, you know it's much easier to make that turn when you have that banking. All right, typically on a banked track, times for running are a lot faster because that banking helps you make that sharp turn. So let's think for a second about the forces we have acting on an object that is traveling on a banked curve. We're once again going to employ our side view here when we're thinking about this. And so, assuming there's no friction, and there could very well be, and there will actually be friction normally, but we'll ignore that for now, we're definitely going to have the force of gravity acting on the object. We're also going to have a normal force going perpendicular to our surface, as always. Thinking about the direction of the acceleration, okay, our acceleration is going to be inward like that. So this looks very, very similar to a situation we've done before, and that's inclined planes. However, you have to be careful because this is different than inclined planes. There's a really, really important difference here, and that is the direction of the acceleration. So with an inclined plane, we typically were sliding up or down the incline, accelerating up or down the incline. However, in the case of a banked curve, we're not. We're accelerating towards the center of our circle. And ideally, if we're not sliding, we're not accelerating up or down that banking at all. We did something really important with inclined planes. Our trick was we would tilt the axis. And one of the main reasons we did that is so that our acceleration, which was going up and down the incline, was in the direction of the x-axis. However, we don't want to tilt the axis here for a banked curve because our acceleration is just to the right, and we actually will be making it more complicated by tilting our axis. So we're going to, instead of breaking up the forces of gravity, or the components of gravity, we're going to break normal force into its x and y components. And whatever our angle is down here, that ends up being this angle as here. We could go through the geometry to prove that, but we'll skip that for now. And so that y component becomes Fn cosine of theta, and the x component becomes Fn sine of theta. All right, and as I was just mentioning on the last one, with inclined planes, we do tilt the axis because our acceleration is at an angle. Okay, for banked curves, we do not tilt the axis because the acceleration is not at an angle. And the x component of the normal force is the thing that ultimately provides that inward force leading to that inward centripetal acceleration. So even though these two situations look similar in terms of their free body diagrams, they are different situations. And that's why it's important to know why we did some of the things we were doing earlier, because in this case, we are not going to tilt our axis. All right, so let's go ahead and work through a practice problem here with an object on a banked curve. So for this problem, we're going to use a bobsled. That's going to be our object going around a banked curve. And we want to know what angle should the curve be banked so the bobsled can navigate the curve perfectly, not sliding in or out of the curve, without needing friction. We're basically going to only deal mathematically with cases of banked curves where we don't have friction. It gets pretty messy when you throw friction into the mix. Now there might be a conceptual question about that, but not really one mathematically. So let's go ahead and start by identifying the forces we have acting on the object as it travels around the curve. We have a normal force going up at an angle like that, and we have the force of gravity going straight down. Okay, and again, we're thinking about this side view where the curve's something like that. Doesn't necessarily have to be a full curve, but something like that. Our acceleration is going to be directly to the right, based off of how I have it drawn, going inwards towards the center of the circle. And so the first thing I'm going to do is I'm going to take that normal force and break it into my x and y components, because remember, we're not tilting our axis here. The angle of the banking is going to be this angle in here, and so that y component is going to be Fn cosine of theta, and this x component here is going to be Fn sine of theta. I'm now going to go ahead and set up my max and my may. So in the x direction, what I have here is I have Fn sine of theta. That's the only force I have, that x component of the normal force. That's what's making it move in a circle. So that's going to be equal to m times my acceleration, which is v squared over r. In the y direction, I have that y component of the normal force, Fn cosine of theta, minus the force of gravity. And that's actually going to be equal to 0 because if I'm not sliding up or down the incline, that means I'm not accelerating vertically. I'm only accelerating inward because it's traveling in a circle. And so that means I can solve for Fn cosine of theta, and it's just going to be equal to mg, because that's what the force of gravity is. I'm ultimately looking for this angle here, theta, okay? And so I'm somehow going to have to combine these equations. There's a lot of stuff going on here. But what I'm going to see that's really nice is I have a sine of theta and I have a cosine of theta. And I know I'm solving for theta. So there's the trig identity that comes into play here, and that is that sine of theta over cosine of theta is equal to tangent of theta. That identity is going to help me out a lot. And whenever I see a sine of theta and a cosine of theta, I'm always thinking in my mind, I need to turn that into a tangent of theta. Otherwise, I'm going to have two thetas, and it's going to be impossible to bring them together, all right, and solve my problem. So the way I'm going to bring them together is a technique that you're probably not that familiar with, but it's something that's really useful in this situation. And that is, I'm going to take my two equations, and I'm actually going to divide the two equations. So I'm going to divide the left sides of the equations and the right side. So I'm going to do Fn sine of theta divided by Fn cosine of theta. The Fn's divide out, and I'm left with tangent of theta. And on the other side, the masses divide out. And what I'm left with is v squared over r all over g. I'm going to multiply top and bottom by r to get rid of that double fraction. And so I get that tangent of theta is equal to v squared over gr. And so I can take the inverse tangent there and get that theta is equal to the inverse tangent of v squared over gr. Moving on to my second question, if the bobsled is traveling faster than that given speed, which way would friction point? Well, if it's traveling faster, that means I need more inward acceleration. So that means my friction is going to be going down the banking, okay, giving me more inward force to allow it to have that greater inward acceleration. In terms of my new free body diagram, Fn and Fg still are obviously there, and now I would just have friction going down the banking. It still does act perpendicular to the surface like it would on an incline. It's just that we're not tilting our axis, but I still do have friction going down that banking to keep it traveling in a circle. If it was going slower, okay, the car would actually be in danger, or the bobsled in this case would actually be in danger of sliding down the banking, okay, if we were going slower than v without friction. So in that case, friction would act up. All right, so what we did in the first part was we found that perfect angle, which is a useful thing to do because in reality, you're obviously not always going to be going at that exact same speed, but friction down the incline or up the incline gives you that little bit of wiggle room to travel a little faster or a little slower than that perfect speed.